Last year, you learned about gravitational force. We compared that earlier in this unit to electric force. The two are really similar in terms of structure, right? They're both inverse square relationships. The equations look almost exactly the same. We just substitute different variables in. The structure is the same. Well, we also learned about something last year called the gravitational field. Today we're going to talk about electric fields, which again are real similar to gravitational fields in terms of the structure and in terms of the way we think of them. I want to go back to gravity for a second, though, because it's a little bit easier to see, to feel, to touch gravity than it is electricity. Electricity force and electricity fields. So let me give you this example here, this analogy here. Okay, I've got a board marker in my hand. This board marker experiences, because of the Earth, a gravitational force. That gravitational force is ultimately caused by, I don't know how many of you guys have heard about this or read about this, whatever. It's ultimately caused by, we say it's a curvature of space-time. Space-time is bent because of the Earth. Heavy things dent the fabric of space-time, and that causes gravity. That causes the force of attraction between the Earth and this board marker, such that if I drop this board marker, if I let it go, then that force of gravity caused by the curvature of space-time that the Earth caused, the board marker will fall towards the Earth. Right? It's basically going to toboggan down the fabric of space-time toward the center of the Earth. Of course, it doesn't go to the center of the Earth because the Earth stops it, right? But it is attracted to the Earth because of that force of gravity that's caused by this curvature of space-time. But if I take the board marker away, then obviously it's not going to slide down the fabric of space-time toward the center of the Earth. The force of gravity is now gone. You guys remember how we defined force way back in grade 6? A force is defined as a push or a pull. That's as simple as that. It's a push or a pull. You define it that way in grade 6. You define it that way in physics 30. You define it that way in your 4th year university. A force is a push or a pull. Simple as that. If you don't have the board marker there to be pulled, then there is no force. Agree? But the thing that caused the gravity, and that is the curvature of space-time that was ultimately caused by the Earth, that's still there. So we still have gravity there. We just don't have a force of gravity. We have something there that we have to describe, but we don't have a force, a push or a pull. So we're going to describe that gravity that's not a push or a pull, but rather is just the curvature of space-time as a gravitational field. A gravitational field is a region in which there would be a gravitational force if there was a mass to experience it. Does that make sense? Okay, right above the surface of the Earth, there is a gravitational field. If I was to put a board marker there, it would experience a force. But the field is there even if there's nothing there to experience the force. We have a similar concept with electricity. An electric force is a push or a pull caused by some other charge. If I was to take the second charge away, there's no longer a push or a pull. There's nothing to be pushed or nothing to be pulled. But the first charge is there. So whatever it was causing is still there. Just like the dent in the fabric of space-time caused by the Earth causing gravity. It's still there. So we're going to define an electric field in a similar way to the way we define a gravitational field. Gravitational field was a region in which a gravitational force could be experienced if there's a mass there to experience it. An electric field is a region in which an electric force could be experienced if there's a charge there to experience it. So let's pretend the Earth is a big charge, not a mass anymore, it's a big charge. The board marker is a smaller charge. If the board marker is where it is right now, if you look up here, the board marker in my hand right here, the Earth, our new big charge causing electricity here, an electrical phenomenon here, there would be a force on this board marker. But if I take that board marker away, the thing that caused it hasn't disappeared. It's still there. But there's no force because it can't push on something or pull on something that's no longer there. But the electrical phenomenon that caused the push or the pull is there. That's what we're going to call the electric field. It's the region around this big charge in which there would be a force if I all of a sudden put that board marker back there. Yep.
So is this where...
Now, a gravitational field always points toward what causes it, right? If this is the Earth, a gravitational field will always point toward the Earth. Why will it point towards the Earth? Well, because if I was to put a mass, let's say right here, it will fall towards the Earth. If I was to put a mass right here, it would fall towards the Earth. Right? The field doesn't need that little red object there to experience it. The field's still there no matter what, as long as the producer's there. But if there was that little red object there to experience it, it's going to experience a force. It's going to fall downward, and that's why we say the field is inward. But electric charges, electric fields, a little bit different. We can have two directions of electric fields because we can have two kinds of producers. There's one kind of mass, one kind of Earth. The field always points towards it. But we have two kinds of charge, positive and negative. If we have a negative producer, a big negative charge, if the Earth had a massive negative charge, the electric field would point toward it. If it was a massive positive charge, the electric field would point away from it. We'll talk more about that in a few minutes. So the diagram for a negative producer, same as the diagram for gravitational field. Diagram for a positive producer, going to be opposite to that, as you're going to see in a moment here. We said that the electric fields surround electric charges, just like gravity fields surround masses. And we're going to say that the electric fields are vector fields, just like gravity is a vector field. Why a vector field? Well, because direction matters. When I put a board marker in the gravitational field, it doesn't move in a random direction. It moves downward. There's a clear direction associated with that field. That is the case with electric fields. It's not the case with certain kind of fields that we call scalar fields, like heat fields or light fields. The light influences me, but not in a particular direction. Heat influences me, but not in a particular direction. All the fields that we do in Physics 30 will be vector fields. We've talked about gravity fields already, electric fields now. We'll talk about magnetic fields in the next unit. They're all vector fields. They all have a direction associated with them. Now, we alluded to this earlier. Electric fields, gravitational fields for that matter, exist as long as you have something to cause them. The Earth causes gravitational fields. It doesn't matter if the board marker is there to experience that field or not. The field is there, as long as there's something to cause it. Here's my producer. Let's make it a positive this time. Last time it was a negative with the field lines pointing towards it. This time it's a positive with the field lines pointing away from it. If I put an object or a charge there to experience it, the field is there. But if I take away that charge, the field is still there. The field is there as long as there's something to cause it, whether or not there's anything to experience it. A force, on the other hand, which is a push or a pull, is only there if there's something to cause it, i.e. there's a field, and there's something to experience it, i.e. another charge. So it would be a situation like this. I've got my positive charge with the field going outwards away from it, but I got this experiencer over here. These diagrams are almost the same. In the top diagram, all I have is a field because there's nothing to experience it. In the bottom diagram, I have my field, but I also have a force. push or a pull on this guy right here. Now let's define the direction of the electric field, which is exactly what Daniel was asking me about before. Why does the electric field go away from the positive? Why does it go toward the negative? Well, Daniel, it comes down to an arbitrary definition. We arbitrarily define a lot of things, like most things in this world, right? We arbitrarily define the color of this water bottle as red. We could call this word anything else, and in fact, in other languages, they do, right? In French, it's rouge. In German, it's whatever. In Italian, it's whatever. We arbitrarily define that as red, okay? We arbitrarily define the direction of the electric field as the way that a positive particle moves when placed in the field. It's similar to gravity field, right? We define a gravity field direction as the way that a mass moves when placed in the field. If I take my board marker, which way is the gravitational field? Well, we said it points down toward the Earth. Why is it down toward the Earth, though? Well, because we arbitrarily define the direction of that field as the way that this board marker will move if I place it in the field. Which way does it move? Down. So the field is down. That's arbitrary. We could have defined it as opposite to the way that it moves, but we didn't. We define the electric field as the way that a positive would move when placed in the field. We could have defined it as the way that a negative would move when placed in the field, but we didn't. We have to have the same definition for everybody. Like, we have to agree on a definition, and this is the one that we, or that other people have agreed upon. Now, we define it another way as well, which fundamentally comes down to the first way, just another way of saying it. It's away from positive and toward the negative. That's, again, what you were asking about earlier, away from the positive toward the negative. Draw a couple pictures here. This is a positive producer. The field goes like this, away from the positive, right? Away from the positive. Here's a negative producer. The field goes toward the negative producer. Why is it that way? Well, because if I put a positive little experiencer there, which way would it move? Away from it. It's repelled by the positive, right? If I put a little positive right here, which way does it move? Towards it. The force over here is outward, so the field is outward. The force over here is inward, so the field is inward. We arbitrarily define it as away from positive toward the negative because the field is the way that a positive particle would move if placed in the field. Tanner?
If opposites attract, and say on the diagram on the right, if you place the positive red thing with a negative.
Yeah, like if I put a negative right here, let's say.
Yeah.
Yep.
And then, so the force would be going towards that negative.
No, the force would be going away from that negative because they're repelled, right?
But what about it in itself?
What about it? Well, the force on the green caused by the producer is away from the producer, right? They repel each other, so the green is pushed away. Does it make sense?
Yeah.
Now, that's opposite to the field, right? Wait a second, doesn't that contradict this? No, this definition says it's the way that a positive would move if placed in the field, not the way that a negative would move if placed in the field. Okay, same thing over here. The electric force here would be inward. The field is still outward because the field is the way that a positive would move if placed in the field. Okay, negatives always experience a force against the field. Positives always experience a force with the field. Got it? Tanner, I'm going to ask you a question. Which way is the force on a positive particle? With the field? Okay, I'm going to ask you that question again. Tanner, which way is the force on a positive particle? Are you sure? Are you sure? Parker? I want you to repeat after me. I'm positive the force is with the field. I'm positive the force is with the field. That's how you're going to remember that a positive particle experiences a force with the field. Does a positive particle experience a force with the field? Yes? Are you sure? I'm positive the force is with the field. Now, if it's a negative particle, the force is opposite to the field. Got it? Look at these diagrams here. Okay, in both cases, the positive, the force is with the field. In both cases, the negative, the force is against the field. Daniel, does that answer your question?
Yeah.
Okay, but you got another one now. Yeah, go ahead.
So if you're writing like a free body diagram, you'd never just write this. You would only write what's relevant to the particles around it.
That's right. Like in one of those questions we were doing like earlier today. Yeah. No, you wouldn't draw the fields. You would just like, I mean, you could, but you just complicate your diagram. Okay, it's just like, if I'm an engineer designing a bridge, like, well, the mass of the core of the Earth is relevant in terms of calculating a force of gravity and the stress on my bridge. But do I need to go into that much detail to calculate the stress of that bridge? No. So you could, but it wouldn't be necessary, and it would be the same thing for that question.